The example then is for a response of an RC integrator to a single pulse when the pulse width is less than 5 time constants. So a single 10-volt pulse with the width of 100 microseconds is applied to the RC integrator shown below. Part A asks, to what voltage will the capacitor charge? B, how long will it take the capacitor to discharge if the internal resistance of the pulse source is 50 ohms? And then draw the output of the waveform. So, as we did before in our earlier studies, we need to calculate the time constant. We need to find out what tau is. So the circuit time constant in this case is tau equal to RC. So 100 k ohms times 1 or 0.001 tens, hundreds, thousandths, 1,000th of a microfarad gives us 100 microseconds. So that's tau. Notice that the pulse width is exactly equal to the time constant. Thus, the capacitor will charge approximately 63% of the full input amplitude in one time constant. So the output will reach the maximum voltage of, so when we calculate this, one time constant, remember from our previous studies, 0.63, we multiply that, that's 63% of the max or the peak voltage, which gives us 6.3 volts. The capacitor then discharges back through the source when the pulse ends. You can neglect the 50 ohm source resistance in series with the 100 k ohm resistor. The total approximate discharge time, therefore then, 5 tau, 5 times 100 microseconds gives us 500 microseconds. Okay, so that's how long it takes the capacitor to discharge if the internal resistance of the pulse source is 50 ohms. Part C then asks us to draw the diagram below. The output charging and discharging curve then is shown. So for the first 100 microseconds we're charging up to 63%, 6.3, and then we discharge out to 5 tau or 500 microseconds. Okay, so there's an exploded view you can take a look at, and you can see what's going on here from what we've seen before, the 63% point of course being there, and then if we go out to a full 5 tau of charging, which we were not given in this problem. So in this case, again, we calculated tau. RC gives us 100 microseconds, and then now we can see here a larger view then with the 1 tau, 2 tau, 3 tau, 4 tau, and 5 tau, the timing constants. Okay, so 5 tau gives us 500 microseconds. So there is our plot of what's going on to 63%, and then out 1, 2, 3, 4, 5 tau. Determine how much the capacitor will charge when the single pulse is applied to the input. So now in this case we're just going to hit this thing one time with a pulse that's 5 milliseconds in width, 25 volts in amplitude. So we calculate again, just like we did before, the time constant, tau, R times C. So we have 2.2 k ohms for the resistor, 1 microfarad for the capacitor, gives us 2.2 milliseconds for tau, 1 tau. Because the pulse width is 5 milliseconds, the capacitor charges to 2.27 time constants. Okay, so we can see here 5 milliseconds divided by 2.2 milliseconds gives us 2.27 time constants. Use the exponential formula then that we saw in chapter 12 to find the voltage to which the capacitor will charge, with V sub F equal to 25 volts and the pulse width T, or T sub W if you want to put the W there, 5 milliseconds. The calculation is as follows. So here's that exponential relationship that we acquainted ourselves with before when we studied this in DC. So the little v, again, that's telling us that this is not a DC voltage. V final, and we multiply V final times 1 minus E to the minus T over RC. So 25 times 1 minus E to the minus 5 milliseconds divided by 2.2 milliseconds. Again, if this doesn't look familiar to you, go back and review the applications that we developed and used back in the DC course. So 25 volts times 1 minus E to the minus 2.27 becomes that value there. So 25 volts, 1 minus, when we take E to the minus 2.27 on your calculator, 1 minus 0.103, then gives us a value of 89, almost 90% of 25 volts, which gives us 22.4 volts. These calculations then show that the capacitor charges to 22.4 volts during the 5 millisecond duration of the input pulse. It will discharge back to 0 when the pulse goes back. Okay, so that's a single pulse. Again, we can look at it here, expanded, might be a little easier to follow. Each of the steps are the same. Take a look at this, pull out your calculator, work through this example, make sure that you understand this, and again that you refamiliarize yourself with the exponential form. So in electronic systems, you'll encounter waveforms with repetitive pulses much more often than single pulses. However, an understanding of the integrator's response to single pulses is necessary in order to understand how these repetitive pulses respond. So if a periodic pulse waveform is applied to an RC integrator, the output wave shape depends on the relationship of the circuit time constant and the frequency period of the input pulses. The capacitor, of course, charges, and discharge response is to a pulsed input. Okay, so that hasn't changed. The amount of charge and discharge of the capacitor depends upon the circuit time constant and the input frequency as mentioned. Okay, so look at the waveform here, study it here. It's given us what the period is, what the amplitude is, and what we expect to see on the output. So if the pulse width and the time between pulses are each equal to or greater than 5 time constants, the capacitor will fully charge and fully discharge during each period, now capital T, of the input waveform. When the pulse width and the time between the pulses are shorter than 5 time constants, as illustrated for the square wave, the capacitor will not completely charge or discharge. We'll now examine the effects of the situation on the output voltage of the RC integrator. So they're showing you here that we have a pulse width then, in this case, that's less than 5 time constants or 5 tau. So for the illustration, let's use the RC integrator with a charging and discharge time constant equal to the pulse width of a 10 volt square wave as shown. This choice will simplify the analysis and will demonstrate the basic action of the integrator under these conditions. At this point, we don't care what the exact time constant is because we know that an RC circuit charges approximately 63% during one time constant interval. Okay, so when we come back, we'll run through the steps here of what's happening from pulse to pulse.